let's do a little bit of a review of what we've done so far with polynomial functions. Well, so far if you've got p of x equal x squared minus 5x plus 6, and you're trying to find the zeros of this function, well, that means that you want to find the values of x that make p of x equal 0. Well, that's pretty easy in this case because you could factor and solve. And we'd get x equal 2 and x equal 3. So that really means that if I put 3 in the place of every x here and did the math, I'd get 0 for p of x. Likewise, if I took this 2 and I plugged it in for the x's, I'd get 0 for p of x. Okay, so graphically my curve p goes to the x-axis at 2 and 3. Not a problem. But let's talk about what problem we do have. What if our function, polynomial function, was instead 2x cubed minus 7x squared plus 5? Well, you could probably see the problem that we have. This polynomial won't factor. So we can't even get to the place where we were up above. I mean, if you want to find the zeros of a function, the only way we know how to do it so far is to get 0 on one side by substituting p of 0 in for p of x and then factoring. So let's now move forward to where we are, and we're going to have polynomials like this where we're still trying to find the zeros of the function. But, you know, I need to come up with some way of knowing, well, what numbers should I even try to plug in for x so that I get 0 for p of x? I mean, where do I even start with this process? So that's called the rational zero theorem. You know, this is a way of narrowing down the numbers that you can plug into x. And the rational zero theorem says that the possible rational zeros, the possible numbers that might be x values, are very simple. Well, they're going to be fractions. And the top number in the fraction will be the factors of your constant. Well, my constant is 5, and the factors of 5 are 1 and 5. And then the denominator will be the factors of your leading coefficient. In this case, mine is 2. And the factors of 2 are 1 and 2. So all combinations of those fractions, let's see, I've got 1 divided by 1, that's 1. I've got 1 divided by 2, that's 1/2. I've got 5 divided by 1, that's 5. And I've got 5 divided by 2, that's 5/2. So I'm going to have all positive values, that's 4 possible numbers that I could plug in for x, and all negative values. So all positive and negative values of these 4 numbers, this is the cool part, are the only possible rational numbers that I could plug in for this x and for this x that just might even give p of x as 0. So we've narrowed it down to 8 values. Okay, this is the rational zeros theorem. And this is, I believe this is part F on the worksheet. So if you're asked to find the possible rational zeros, you take the factors of your numerator, the factors of your constant, that's the numerator of all the possible rational zeros, and then you take the factors of your leading coefficient, that's the denominator of your possible rational zeros, and then of course all combinations of those numbers, 1 over 1 is 1, 1 over 2 is 1/2, 5 over 1 is 5, and 5 over 2 is 5/2, and you take all positive and negative values of those. Okay, so that's how you find the possible numbers to plug in for x. Now, how do we figure out which of those 8 are actual zeros? Well, let me rewrite my p of x because it's gotten kind of messy. My p of x is 2x cubed minus 7x squared plus 5. Okay, well, I mean, I could go to the trouble of literally plugging 1 in for every. I could plug those 8 numbers in for x. Okay, so I could find p of 1, do the math. I could find p of negative 1, do the math. Plug negative 1 in for x. I could find p of 1/2. Holy smoke, I really don't want to do that. Plugging 1/2 in for x and then plugging it in for x both places, squaring it, gets some crazy fractions. You know, ultimately I want to see which of these on down give me a 0, but that could take 40 forevers if every time I have to plug in these x values, cube it, multiply it by 2, square it, multiply it by -7, add 5, and see if I'm getting 0 as an answer. There's got to be an easier way. There's got to be an easier way than plugging all of these 8 numbers in for x to see which one gives me p of x equals 0. So that's what I'm here to tell you, is that there is an easier way. And that easier way is what we're going to call synthetic division. Synthetic just means fake, so we're doing fake division. Okay, so I'm going to test to see if 1 is a 0. 1 is one of my possible rational zeros. I'm going to do the positive 1. So I'm taking the 1, and I'm going to write it down over here. And with it, I'm testing to see whether 1 is a 0. And along the top of this little chart that I'm creating, I'm going to put the coefficients of my polynomial, coefficients. So I've got a 2, and I've got a -7, and I'm going to need to put a 0 and a 5. So I'm putting a 0 here because I don't have an x term. And in synthetic division, when you are missing a power of x, you need to put 0 placeholders, just like you did in long division in 4th grade. Okay, so here's what I got. Here I go. Here's my synthetic division, fake division process. Bring down my 2. Then I'm going to multiply 2 times 1, that's 2. Add it to -7, and write down the result. That's -5. So 2 times 1 is 2, plus -7 is -5. -5, continue this. -5 times 1 is -5, plus 0 is -5. -5 times 1 is -5, plus 5 is 0. Now, since I got 0 here, this is really the remainder of the division. Okay, that's nice. But since I'm getting 0 as a remainder, that means that p of 1 is 0. So 1 is a 0 of p. All right, that's 1 of 3. 1 of 3. Let's check. Let's try the -1. So up here, I've got that -1 might be a 0 of the function, so let's try the -1. Let's see. I'm going to try -1. Let's do that in purple. It's my -1. Okay, again, I'm going to bring down the 2. 2 times -1 is -2, plus -7 is -9. -9 times -1 is 9. 9 plus 0 is 9. 9 times -1 is -9. Plus 5 is -4. Okay, so what does that tell me? Well, that tells me that P of negative 1 is negative 4. So x equal negative 1 is not a 0 of P because I'm not getting something other than 0 for my remainder. Getting something other than 0 for my remainder. Let's try another one of my list of 8 numbers. What about a half? Let's try a half when x is a half. I'm going to bring down the 2. 2 times a half is 1. 1 plus negative 7 is negative 6. Negative 6 times 1/2 is negative 3. Negative 3 plus 0 is negative 3. Negative 3 times 1/2 is negative 3/2. That's negative 1 1/2. Negative 1 1/2 plus 5 is 3 1/2. All right, what does that tell me? That P of 1/2 is 3.5. Therefore, 1/2 is not a 0 because I'm not getting 0 for P of 1/2. All right, let's try negative 1/2. Bring down my 2. 2 times negative 1/2 is negative 1. Plus negative 7 is negative 8. 8 times negative 1/2 is 4. 4 times, let's see, negative 8 times negative 1/2 is 4. 4 plus 0 is 4. 4 times negative 1/2 is negative 2. Negative 2 plus 5 is 3. Therefore, P of negative 1/2 is equal to 3. Negative 1/2 is not a 0 of the function. But if I had gone to all the trouble of taking this negative 1/2 and plugging it in for x here and here, and done the excruciating math of squaring fractions and multiplying and coming up with a number, I would have gotten 3 when I was done. So what does synthetic division do for me? Well, in a very quick, easy way, you're able to test your possible rational zeros without having to go to all the work of plugging those numbers in for x and doing the math. Imagine if your polynomial was 5 or 6 terms long and you were having to put in, 8 or more numbers every time. That gets very tedious. But I'm going to try to see if I can find another 0 from this list. I've already found one. Let's try the 5. When x is 5. 5 is in my list. Up there on top right. 5 is in my list. Let's try that. I'm bringing down the 2. 2 times 5 is 10. 10 plus negative 7 is 3. 3 times 5 is 15. 15 plus 0 is 15. 15 times 5 is 75. 75 plus 8 is 80. Okay, that's definitely not a 0. But I do know that P of 5 is 80. Well, okay, 5 doesn't work. Let's try negative 5. Negative 5 was in my list. 2. Bring down the 2. 2 times negative 5 is negative 10. Negative 10 plus negative 7 is negative 17. Ooh, negative 17 times 5 is 105. 105 plus 0 is 105. And 105 times negative 5 is not negative 5. I would have to get negative 5 to add it to 5 to get a 0. So I don't know what it is, but it's definitely not equal to 0. So let's try 5/2. Positive 5/2 was in my list. Bring down my 2. 2 times 5/2 is 5. 5 plus negative 7 is negative 2. Negative 2 times 5 halves is negative 5. Negative 5 plus 0 is negative 5. Make sure I got that right. 5, negative 2, negative 5. Yeah. Negative 5 times negative 5 halves is negative 25 halves. Negative 25 halves plus 5 is not going to give me 0. Okay, 5 halves doesn't work. I'm out of room, so let me try negative 5 halves on that same line. I don't want to lose the top of my chart for you. So 5 halves doesn't work. The last one I need to check is negative 5 halves. So I've got a 2. 2 times negative 5 halves is negative 5. Negative 5 plus negative 7 is negative 12. Negative 12 times negative 5 halves is, let's see, that's 30. 30 plus 0 is 30. Okay, 30 times negative 5 halves is negative 75. Negative 75 times 5 is negative 70. Okay, so negative 5 halves is not a 0 either, but I do know that P of negative 5 halves is negative 70. So the moral to the story is that through this process of finding the possible rational zeros, there were 8. I got to have 3 zeros total, first of all. I got to have 3 zeros. 8 numbers were possibly the rational zeros. I have found that 1 is a 0 of the function. So the other 2 zeros are kind of hidden right now. We'll have a way of finding that, next week or in the coming days. But I know that 1 is a 0 because I'm getting 0 in the remainder in synthetic division. But in addition, I also found other values of the function. For instance, the point negative 4 is on the graph of this function. But I just know that negative 1 is not a 0 of the function. My function is not going to cross the x-axis at negative 1. So through the use of synthetic division, I'm ultimately looking for these remainders of 0 to show that I'm getting a 0 of a function. But if I don't get zeros as the remainder, I still, by the remainder theorem, are finding function values.